Hi again. This is Tim Shu from San Jose State University here to talk today about Newton's method. I'm going to start with the most important thing, which is that I want everybody to understand what it is that Newton's method does, what the point is. I'll describe the algorithm for Newton's method, and we'll work an example. Okay, so the most important question again, what is the point of this Newton's method? What is the goal of Newton's method? What problem does it solve? Well, so the deal is, so given a function of f of x for which we have a formula, suppose we have some function f of x, and we know a formula for f of x, that's pretty important. What Newton's method does is to find a solution for f of x equals 0 that is close to some initial guess x1, or at least we hope it will. It's not guaranteed to work exactly, but it does in many cases. So it's easy to get lost in the details, and of course when you use this, you're very concentrated on, I want to find that solution and work the thing, but keep in mind what the whole point is. The point is to find a solution for f of x equals 0. Okay, so here's the basic idea of what's going on with Newton's method and why it works. So suppose we want to solve f of x equals 0, and we have some guess x1, some particular value of x that we think is close to being a solution to f of x equals 0, but isn't quite, perhaps. So the basic idea of Newton's method is that we have good reason to suspect, as we'll see in a minute from a picture, that the tangent line to y equals f of x at x equals x1 will intersect the x-axis, but not quite at, but close to where the graph y equals f of x does. So, the part where that is the x value where the tangent line intersects the x-axis is going to be very close to the actual solution that we want. So to see why we might think that, let's look at an example. All right, so here we have an example. So just for now, a random curve with its tangent line. And we see that because we're looking at a region of the graph that's close to an intersection of our desired graph, y equals f of x, and the x-axis, we're sort of close to a solution to f of x equals 0. That would be it right here. And so because the tangent line itself is close to the actual graph, that means the place where the tangent line intersects the x-axis is close to, well, kind of, close to where the actual graph intersects the x-axis, and so we might hope that this is going to be some approximation of what we want, a solution to f of x equals 0. Okay, so again, returning to our main discussion, we're trying to solve the equation f of x equals 0, and we have some near solution x1, that's the assumption, that's our starting place. And so remember, the tangent line to y equals f of x at x equals x1 has slope, do you remember? Yeah, that's right. The slope of the tangent line is f prime of x1. And that tangent line goes through a point. Well, do you remember what point? If you remember there's one point that the tangent line can be sure to pass through, it is? That's right, the point on the curve with x value x1, so that's x1 comma f of x1. So its equation is, from the point slope formula, y minus f of x1 is equal to f prime of x1 times quantity x minus x1. So you go, remember the point slope formula means you plug in the point over here, and the slope of your line goes over there. So that's the equation of the tangent line at x equals x1. And so to find the x-intercept of this line, we set y equals 0, and we solve, getting, and I'm going to omit the algebra. You should go do it yourself. That's more interesting. But you don't really need to know it anyway. The final solution that we get for the x-intercept of this line, which is x equals x1 minus quantity f of x1 over f prime of x1. Kind of random looking, but that's what we get from this procedure. And so, really actually my point in going through this procedure is that if perchance you're on an exam, you forget what the formula for Newton's method says, you can kind of recover it by this tangent line idea. All right, anyway, so let's call that number x2. Remember, we started off with some initial guess x1, and we call this new number x2. And the point is that from that picture that we saw earlier, we hope that x2 is closer to a solution, and so x2 becomes our new, and we hope, improved guess. All right, so what we do in the full algorithm, we just do that over and over until, hopefully, we get something pretty close to a solution. That is, we start with initial guess x1. Our next approximation from the formula that we just saw is x2 is equal to x1 minus f of x1 over f prime of x1. And then we just keep doing that. So our new guess becomes x2, and we do the same thing. Our third approximation becomes x3 equals x2 minus f of x2 over f prime of x2, and so on. So in general, if we already have approximation number n, x sub n, then approximation number n plus 1 is going to be x sub n plus 1, which is equal to xn minus f of xn over f prime of xn. So this is n equals 2, this is n equals 1. All right, so we keep doing that until we're happy, basically. But to be more specific, until, for example, those x values, those approximation values, don't change very much anymore. And what do you mean by not very much? Well, that kind of depends on how accurate you want the approximation to be. In general, if you actually were to use this to make money, which people do, I mean, this is what a lot of computer systems use, is Newton's method. The criterion that you choose to stop sort of is based on what you need to happen. But for us, we keep doing this until the x's don't change very much anymore. All right, returning to our actual example. So let's try to find a solution to x to the fifth plus x minus 16 is equal to 0 using Newton's method. So here's the graph of f of x equals x to the fifth plus x minus 16. And we can see that there seems to be a solution around 1.7. Oh yeah, and here's f of x, and here's f prime of x. If you're really doing this, you'd guess 1.7, I'm pretty sure. But just to make this more interesting, let's get started with a guess of 1.5. So that's not a solution to f of x equals 0, because you plug it into f and you don't get 0. In fact, it seems to be pretty far off. But if you plot the original graph and its tangent line at x equals 1.5, this is what you get. And so the second approximation, x2, is this point over here, the x-intercept of the tangent line at x equals x1. All right, so here's our new guess, x2, and remember, and it's using the same formula, x2 equals x1 minus f of x1 over f prime of x1. And so we get x2 equals, that looks better, 1.7 something. I mean, this seems better from the graph, but in principle, if you're actually going to do this with a computer, the computer doesn't have the graph and can't sort of see it, and so all you can do is use those formulas. So this is better. The error seems it's only off by 2.7 as opposed to 6 point something, but still not quite f of x equals 0. Okay, so as before, we're going to use the red tangent line to approximate the green graph and take our new intersection point over here as our new guess. So our third approximation, x3, is the x-intercept of the tangent line at x2, which by our same formula, x3 equals x2 minus f of x2 over f prime of x2 is 1.706, blah, blah, blah. Well, this is starting to look pretty good because f of x3 is still not 0, but it's much smaller than it was before. So again, here's the tangent line plot. And we're going to take this tangent line intersection and make that our next guess. So there's a fourth approximation, 1.70 something something. Ooh, f of x4 is looking much better. 3 zeros, 0.3 zeros, and a 7. Okay, same thing again. And we get x5, and f of x5 is very small. It's 3 times 10 to the minus 8th. So this is looking pretty good. But just to make sure, just one more time, we're going to get a sixth approximation. And as you can see, so x5 was 1.7023656111, and x6 is 1.7023656110. So it really hasn't changed very much at all. I mean, f of x6 is even better. It's minus 1 times 10 to the minus 8th. But I think, at least for our purposes now, we can pretty much say, well, we're pretty much done. And so because our approximations seem to be stabilizing at around 1.7023656110. So fine. That's roughly a solution to what was it you were trying to do? Remember how I was saying it's very easy to get lost in the details and forget what the point was? Yeah, the point is that it's very roughly a solution to x to the fifth plus x minus 16 equals 0. And if you indeed plug in 1.7023656110, you get approximately minus 1 times 10 to the minus 8th. So great. Okay, so that's it for now. Go try Newton's method yourself, and thank you very much. Bye.